Hello, my name is Martin Mosier. This is for Triple E 120, Lab 3. Today is November 7th, 2024. This lab is a week late for me, so I will be getting 10% off my grade on this lab. So at most, I can only get a 90. So we are asked to create some registers, some counters, some RAM, and the brainless CPU unit, central processing unit, with a bunch of components that we made in our previous labs. So our first component that we built was the 4-bit D flip-flop register. So it's using 4 D flip-flops, some splitters, 4-bit mux, and 4 inputs. Basically what we put on D won't go to Q until we press enable and clock increments. Reset sets Q to 0, and if enable isn't on, what's in Q will get outputted instead. So Q doesn't change until enable, and D changes as well as clock. Here's the waveforms. I did a couple of tests on here. One just to make sure that nothing would change if enable wasn't on, so enable is set to 0. Clock changes, but D is 8 and output does not change to 8, which means that's working. Then I had some tests done on reset. I set reset on 1, which sets Q to 0, and then I changed D to the values of 1, 2, 4, and 8 to make sure that each of these flip-flops were working individually, and then I reset it once more, and then set all of these to, I set D to F, just to make sure that all of these flip-flops could work in tandem. As you can see, everything works properly. Then we made a 4-bit counter, basically using the 4-bit register that we just made and an incrementer. We take enable once it's on, the incrementer goes to D, and basically every time clock increments, Q increments up by 1. Reset sets Q to 0 again, so it would go from 0, enable is 1, when enable is 1, clock, it'd go up to 1, clock, go up to 2, clock, go up to 3. After that, we made 4-bit RAM, so our program RAM. It has an address, a data in, a write, and a clock. Clock works basically how everything does, how everything else has in the components. Every time clock increments, then something changes, unless we don't have enable on. Basically, in this case, enable is write, but write also does one more thing. Whatever is on data in, if we have write on, when clock changes, whatever is in data in is written to the address that is defined in AVDR address. So we have a file called ramvals.hex that we put into digital. It basically tells us that when we simulate this program RAM, that it's going to start with those values. So in address 0 will have a value of 3, and address 1 will have a value of 5, and then all the other addresses will have values of 0. But if address was, say, 2, we had data in as 8, we had a write as 1, and we changed clock, then in address 2 we would have the value of 8 now stored in the program RAM. And then data out just outputs whatever the address is, whatever the value is on the address. Finally, we designed our brainless central processing unit, our CPU. Today we acted as the brains of the CPU, so we have a bunch of inputs for each of the components, and then we have we have 3 total outputs. So we have 5 components. We have our ALU, our 4-bit register, 2 4-bit muxes, and our program RAM. So once again, we have that file set up here so that on program RAM there are some predefined values for the addresses. So again, for 0 we have the value of 3, so address 0 we have the value of 3, and address 1 we have the value of 5. So we can change the addresses that we're looking at with address bus. And then with data in, if we're not trying to look at the RAM or the values in the RAM, once we have data in, that will go to the data bus. So change it to 1. With nothing on, we'll have data bus is outputting to 1. If we do want to read the RAM, we'll set the address to what we want, and then we'll press read, which will change the mux to to reading in B, which will read from the program RAM, and it will send that to the data bus. So if we have 0 on the address, we read it, then we'll have 3 on the data bus, because that is the value stored on that address. We can write to the RAM from the data bus. We can send things into the ALU to add and invert or negate them. That's why we have the invert, arith, and pass, all to control those inputs on that. We have load accumulator, which is what we call our 4-bit register, so we can load values into it. And it'll output it to accumulator, so we can load whatever we have in the output from ALU into accumulator. It'll be loaded into the output, and then we can have accumulator to database. If we want to store a value from accumulator, we can put it into database, and then we can write that into the RAM. We were asked to do multiple tests for it. Here's a waveform. I have some of the tests, so we created additional tests. The default test was add numbers, which was already given to us. Basically, we took the values 3 and 5 from the program RAM, we pushed 3 to the accumulator, and we added 5 to it. Then I did accumulator to RAM just to make sure that the accumulator to database worked perfectly well, and then we could write it to the RAM in whatever address we wanted. I wrote it to address 2, and I wrote 8, which was the value that we got in the accumulator from 3 plus 5, and then I reset it and read it once more just to make sure that 8 really was inside the program. So as you can see, 8 was outputted to the data bus when we were reading, and the address bus is 2, which is what I put it on, so it works perfectly well. And then I made sure that we could write from RAM from data in, so my data in was 6. I read it, I put it on the data address of 3, and then it got put onto the data bus, and then I just read it to make sure that RAM was on it, which it was, and then I pushed 6 into the accumulator so that we could see the 2's complement of it. The 2's complement of 6 would be A, so we can see that that worked perfectly well. And then like in the ALU, it does 2's complement once, and invert and arith are on. And then finally, I ANDed the value of A in our accumulator with the value of the RAM in address 0, which is 3. So A is 1010, and then 3 is 0011. So they share a common value of 2, and thus in ALU out we have the value of 2, which is the AND of A and 3. Here's the waveforms for the add, for the accumulator to RAM, write to RAM, so the 6 to RAM, 2's complement, and then the AND. So yeah. There weren't any bugs or major errors on my thing. There are a couple problems all put into the template, and that's it. Have a wonderful day.